So in this video, I'm going to show how to analyze single molecule tracking data in ImageJ using TrackMate. So I have the movies that I recorded on the microscope. So here is the HRAS 184 single molecule tracking data, and the files that started with 202, they are recorded at the same position. So I want to analyze these movies at the same time. So it will be these 4 files. So I opened by dragging those files and dropping onto ImageJ. The first thing, what I'm going to do once images are all loaded, so I'm gonna combine these images. So there is a function called concatenate. So I'm gonna run this function to combine all 4 images into one. I don't need to keep the original image, so I click OK. And then I'm gonna save this one. So saving the combined image is important, especially when you want to save metadata from TrackMate. So I'm gonna save this image into the folder that I created inside the master folder with the same file name. I just add combined at the end so I can recognize which files got combined into this folder. So I'm gonna save it. It's RAS 184. Let me see. I don't see the folder though. Okay, here we go. Okay, and then I'm going to adjust image property. So you see here, this is actually 4 different time frame stacked with 500 of G stack. So this is not true. So we're gonna change this one to 2000, and then so each image pixel corresponds to 0.108 if you use 100x 1.5x magnification, and time interval will be 1.217 1.0217. This is 21.7 millisecond. Let me click OK. So just check your image if it's got nicely combined. So this checking process isn't necessary, especially if you have the combined different files, and then you may notice that in the previous window you have 2 stacked scale scroll bar. One is for G stack, the other one is the time stamp. So you have to check this one whether it's got correctly combined in series of the image. Sometimes it combined alternatively. Okay, so at this point I'm gonna save the image again. So you can actually save the image at this point, not earlier. I replace. Okay, and then I'm going to run ImageJ TrackMate in here. Sometimes you may see that your image is not clear. So in that case, you can adjust the contrast, image adjust and contrast. Okay, you can make it a little bit better. And then you should be able to see all the parameters that you entered. I think this is fine. I click next. And then we use DOG detector and then next. And then make sure you click both mean, median filter and subpixel localization. I think this estimated blob diameter determines what kind of how large circle you're gonna use to detect the particle. So this one was converted to micrometer scale, so it's roughly 1 micrometer. So I'm gonna put the 0.9 micrometer. It's not the pixel actually, because you convert the image property in micrometer scale. And then threshold here, I know that it typically works around 100. So I may adjust a little bit, just play with a little bit more. Okay, if you put the too low threshold like that, you may detect some spurious particles. So we don't want it. So you increase the threshold gradually, and then you know this one got disappeared, and then now you have 73 spots. 70. You lose some particle over here. That's because the illumination at the edges are not as strong as the center. That's fine. You may a little bit increase this one more. Okay, so still it holds 22. So you should be able to see some range of the threshold, which does not really change the number of the detected particles. So I like around 100 for this image, I think. So I lose some spots around here, mostly edges. Those are fine. Okay, I lose one more spot over here. I think 120 should be robust. And then you can check this parameter setting while you going through the next frame by, I just click the image and then click the right arrow and then click the preview again to see whether these settings are good for other frames. Sometimes I go to the next movie. You may have different parameters for the next movie. Okay, I think everything is fine. So I just go next. Now it's detecting the particles. Just to explain a little bit more, what we are doing here is, so you can use either Igor or MatLab to analyze the data. So here we will use only Igor to analyze the single molecule tracking data. Depending on whether you use Igor or MatLab, the image property setting is different. When you use Igor, you actually put the all real physical parameter, how many micrometer corresponds to the pixel, what's the time scale of this image. But if you use Igor, you just type everything one pixel, width, height, depth in 1 second, because in MATLAB we have a user input that can define the pixel dimension and time scale, and also region of interest. We can do a lot more in MATLAB. So for this demonstration, I will use only Igor. Actually, this is the method I used most for my previous publications. So let's start with the simple tutorial with this, and then we will also work with MATLAB. Okay, it's done. So you can apply initial thresholding to filter out spots, but we are not using it. Hyperstack displayer is fine, and then as I mentioned, we don't filter out spots. And the lab tracker, yes. And then so here is actually micrometer dimension. So you need to enter what's the maximum expected displacement for your particle. So it really depends on how fast your particle is moving. So here for HRAS case, of which diffusion coefficient is around 3, I'm gonna put around 1.5 micrometer. Okay. And then I will not allow the gap closing. The gap closing means you can, let's say you have one trajectory, and then one of the frame, the particle disappeared one of the frames. So basically, essentially, you have the two broken trains, so trajectories. So these two trajectories can be combined if you allow gap closing, but we are not doing this one. So this is kind of very tricky. So if you want to use this function, you have to talk to me so we can discuss case by case. Okay, and I have a trajectory, nicely built. And then to use a TrackMate data in Igor, we have to filter out some immobile particle or very short trajectory. But in MATLAB, you don't need to do that. So since we are doing this analysis for Igor, we are going to apply filters for tracks. So very first parameter that I want to use is number of spots in tracks. So you can scroll the threshold, anything, any data within this blue shade area will be accepted. So you are going to accept most of the particle. So it is actually quite difficult to see. So what I'm going to do is invert, and then I'm going to limit the length of trajectory at least 2 frames. So all particles detected only 2 frames will not be accepted. And at least if we have 3 spots detected, and then they are connected into 2 links as one trajectory will be detected here. Okay. So you can actually see how it changes if you increase the number of spots in tracks. So what you notice is that most of the short trajectory is located at this peripheral region. So first thing is the illumination is not homogeneous. So this side areas has much less intense light, so it's difficult to visualize particles. So your particle may disappear easily when they are located inside. And also you see some trajectory accumulated here. That happened because your particle just disappear and then re-enter, disappear, re-enter, which create a very small number of spots in track. Basically, you break the one trajectory into multiple trajectories. And I think this image, I think we close the shutter at this point, so there is no trajectory beyond this point. So anyway, I'm gonna set this one around 2.8 and then accept all particles, all trajectories that has at least 3 spots. And I also want to remove the immobile trajectories, so you can set the mean velocity here, and then over course we want to see what we're gonna filter out. So as you move this one, you will see some trajectory, some long trajectory will appear if you reach this region. So I'm gonna set this threshold when some long trajectory just appear. Okay, a little bit longer trajectory start to appear. So maybe around here. That's gonna be 11.8, 11.95 here. I like this one. And then we're gonna accept all the other particles. For example, in this setting, you see the dots here. That's actually trajectory, but just particle just stay here. There was not this particle was not moving, so it got detected as immobile particle. And this one is extremely slow diffusive particles. So this one you don't also want to accept. So I'm not gonna accept all this particle here. So I will invert the selection. Okay. And then click next. And then you can save the data here. Okay, so I'm gonna save this one in the folder that I saved the combined movie. Okay, I saved all these 3 files. Once you save, you see the CSV here. And also you can save the TrackMate metadata in the same folder. So if you have a TrackMate metadata in the same folder, and if you don't move your ImageJ file out of this folder, you can actually open the ImageJ and also process the window up to this line. Okay, up to this line. I'm gonna resume, and then there is another way you can save the data. So particularly this one, export all spot statistics, this is not available in previous analysis button. So I'm gonna execute this one. I don't think I use this data for this analysis, but I just show you how to export all spot statistics in TrackMate. Okay, I'm gonna save this one too. Okay, so one thing very important is you keep your record for analysis parameter. So I have Excel, so I can tabulate the analysis parameter that I used. So I'm gonna copy and paste the table that I used for the other sample, and then I'm gonna change some cells. So here I analyzed this set of data, right? So you need to enter this data, right? Okay, so let me correct this one. So I wrote down the date here, but it's not a good idea because you have experimental code. I'm gonna write down the date and also experimental code. Okay, this one into all this stuff. Okay. And then in this experiment, I have this protein, Yesenia made it, Alexa 647 GPP MP label, and then this is on the label, the protein. This is RAS density. But we actually want to enter the actual number of the RAS density, but at this point we don't know the RAS density. So I just typed in how much RAS I incubated, and then time interval is 20 milliseconds, right? Okay. And then Okay, so we analyze the entire data set, right? Oh, by the way, so I have to write this way. So here, this is O2S14. When O2S14, there are multiple images, so I analyze this one, right? So I'm gonna enter this file name as well. Okay, so so that's good. And then I use entire image area and node pre-treat for this analysis and 0.9, and then I know that I did 120. I used median filter, yes. Do sub-pixel localization, yes. Okay. And then I didn't do initial thresholding, and I lab tracker, and the max distance was about 1.5 micrometer, exactly 1.5 micrometer, and gap allowance, no. And then number spot, I think we limited to, let's see, we limited it to 2.84 and 11.95. 2.84 and 11.95. Okay. So that's pretty much for the table. So with this table, you can exactly produce what you did. So I'm gonna save this table and then open the feature again. So we already saved all the data, so that's fine. So I'm gonna finish the recording. Okay, if you have any questions, let me know.